Morning, everybody. Sorry for ruining your morning. I'm David. I'm an SRE that's super paranoid. And a lot of people think that I have an attention to detail, and a lot of times they just think yo, you're crazy, you're weird. But today, I wanted to take this paranoia of mine and I hope to bring it to you all and give you a systematic approach to thinking about building reliable systems based on being worried about everything breaking underneath you. So first, Dropbox. We're a huge storage and sync service. We have over 300 million users. Cool, I said all the things that our PR people would want me to say. Whatever. I want to move on and say one important highlight behind Dropbox, and that's trust. So fundamentally, Dropbox is built on trust. Our users trust us to hold their precious data, and if we've lost their trust, then we've lost the whole business. So really, trust. Trust is our entire foundation. And this talk isn't really about paranoia in the title. That title is just link bait. I tricked you all. Really, this talk is about building trustworthy infrastructure. So let's start looking at that infrastructure. I want to give you an at-a-distance view of what Dropbox looks like. So we have users on the edge, and they talk to a tier of services that hold no state. These services, when they do need state, like data or information about files or users, they talk to a backing tier. And this is separated into two planes. There's the metadata plane, and there's the data plane. And inside of these planes, we use different data stores depending on the problem. So for instance, users or file metadata information, these are stored in different ways on different platforms. Today, though, I'm going to talk about block store. So just that one corner of this whole universe. So what is block store? Block store is Dropbox's own in-house storage for user file data that's designed to scale to exabytes of storage. So in-house, we run the data centers. We run the network on top of it, the software on top of it, all of it. And in building this, I want to highlight one priority of ours, and that's durability. Block store's resilience to data loss, because ultimately, that's our users' trust. And focusing on durability and trust is a big trade-off. For instance, we heavily sacrifice speed of development in order to focus on durability. So I'll give you the rundown for the rest of the talk. Water first, though. There's going to be two major pieces here. There's going to be the architecture first. And the architecture behind block store isn't the main story. But you're going to need the context so you know what it is that I'm actually worrying about. And then this is going to set us up to talk about specific examples of my fears, my team's fears, and how we combat these fears to build that trustworthy infrastructure that I was talking about. And most of the meat is going to be in this second section. And these two pieces are the entire talk. So first, the architecture behind block store. So in Dropbox, we store files. Duh. The way we think about these files is that we break them into blocks, independent blocks, each with a key that describes where that block came from. And handling of keys and organizing them, associating them with files, all of that is in the meta plane, not block store's problem. Block store, we just care about keys and the blocks. And our clients need to do these three major operations. They need to store their data, they need to get it to, and they need to be able to delete their data, because when users remove their files from Dropbox, we'll remove it also. So now, let's zoom on in. So block store has a notion of a zone. And a zone can be thought of sort of as a data center, but not necessarily. A zone certainly is correlated with a location, though. And we have several zones. Zones are geographically spread out, and every single block of data lives in at least two zones. So if we were to lose a zone, it's gone. The aliens melted it. That sucked. Every single block lives in at least one other zone. Furthermore, block store is a multi-master system. Clients can talk to any one of these zones, and upon a write, block store internally is going to replicate those blocks to the other zones as it needs to. So let's take a look at a zone. So it's pretty empty. It turns out we have no computers in our data center, but not really. Let's build up from here. So we need servers to hold the blocks. These are the storage nodes. Then we need to know which storage node has which block, because there's several of these storage nodes. And that's the job of the block index database. So we want to answer, for a key, what storage node is the corresponding block on? And that's stored by the block index database. Then we need to populate these databases and storage nodes somehow. And that's the job of the front-end cluster, which is the gatekeeper to this whole system. So for puts, gets, and deletes, the front end says, hey, block index database, which storage node should I talk to? And the block index database says, oh, this one. And then the front ends can talk to the appropriate storage node. But this isn't quite right. We actually, as a protection, replicate several copies of every single block, or inside of a zone. So the front end has to talk to several storage nodes. And then there's one final piece about architecture before we can move on to the real meat of this talk, and that's how does data get to the other zones? Well, after a write, we have these nodes called the replicators. And replicators watch the block index. So after a put, the replicators will notice that that data's been written, and then it can write it out to the other zones. And there it is. That's the architecture. Breathe it in. I threw out a lot of details, like we have like fancy optimizations and stuff, but like none of those are the point. Don't worry about it. Whatever. What's the real point of the talk here? Well, that's this section, Paranoia, taking fears and combating them to build trustworthy infrastructure. So I wanted to try to define what is it that scares me. So I thought moving things are scary. For example, spiders are scary. Interns are scary. But why are interns so scary? Well, moving things create accidents. And accidents are what scare me. Accidents are what take down the site. They break all the hard drives, all the scary things in life. But there's too many types of accidents out there to consider. And it's not really possible to worry about everything ever. So we need to prioritize. So how do we pick what's worth actually worrying about? And I like to use this scheme of chance and severity. And we can combine these to understand the real danger of an accident, or like how much scaredness to have. That's how I really think about it. Someone maybe change the slide. I made you some examples, though. So alien attack. All the humans are enslaved. I don't really care, but I do care. I mean, I guess death is kind of unfortunate. But why don't I really care? And that's because the chance is really low. It's not worth worrying about because it's probably not going to happen. Another example, some operator reboots the wrong server because you hit the letter M instead of N and didn't see it, something like that. This happens all the time. It's so easy to happen. And that node that's rebooted will go down, but at least the data will still remain. So there's nothing like permanent that we've lost here. So something like this can harm our infrastructure, and it's absolutely worth protecting, but it's not an absolute critical concern. But how about this? A major automation accident. Some scheduler goes, picks the wrong hard drive, something like that. It'll probably happen. Maybe like once a year, like I have no idea. It's really, really scary. The impact can be humongous because if we lose a user's data, we've lost their trust. So worrying about a problem like this, automation going wrong, that's absolutely worth tackling. So following this scheme, I put together my biggest fears. General categories of what it is I'm afraid of. So first, software. Software bugs like spurious deletes, writes subtly failing or like corrupting data. That's pretty scary. Hardware. Hardware is literally moving an actual physical part. Rats bite through wires, hard drives crash all the time. I'm pretty scared of that too. Human operators in production scare me a lot because it's really easy to make small mistakes. But human operators get a lot done, so there's a bit of a trade-off to worry about here. And then automation. Automation does similar things that humans do, but a lot faster. Like that notion of the scheduling bug, refiring every single hard drive. I'm pretty scared. Hope you are too. But here we go. So here's our list. What do we do with this list? Well, I can't really live like this. Like, we don't just have the fears. There's no point in just that, like being afraid of interns. I'd say there's two things to do with your fears. And the first is to verify. We need confidence that our systems are doing what we think they're doing. And verifications are systems that can enable this confidence. And it really is all about the confidence. So in SRE, we talk a lot about monitoring and testing and such. These are examples of verifications, and they're wonderful. But verifications go so much more than just that. And then once we have verifications, then we can go and build protections. And protections are features or systems that can avoid future danger. Essentially, we want to take accidents, and we want to reduce their chance, or we want to reduce their severity. And if we've done that, then we're going to be safer. So here's this list again, and through the rest of the talk, my plan is to apply verify to these, apply protect to these, and show you real examples of what we've done for block store. There is one more fear here, though, that I didn't mention, and that's that I'm afraid of the protections themselves. And why would I be afraid of protections? I'm going to leave this for the end once you have some concrete examples of real protections. So first, I'll dive into software. This is the most dangerous piece to me, so it's going to be the longest subsection here. And I'm afraid of it because it's such a big moving part. We're always building more features, trying to improve performance, all of that good stuff. But with all that comes bugs. So what are you going to do? Well, let's apply verifications. Does this code do what we wrote it to do? So testing. Testing's a wonderful start. Testing gets enough marketing around here anyway, so I'm not going to dive too deep on this. But I have one special point that I want to make, which is that node failure, bugs, these aren't edge cases. In block stores tests, we knock over servers. We make fake bugs by mutating live variables mid-execution. And in these situations, the full system needs to remain healthy. These things are going to happen in production, so you need to test for it. And so tests are great. But a bigger fear to me is actually subtle bugs making it out to production. And so, story time, hooray! I want you to concretely understand what kinds of things I'm actually afraid of. So here's a story back from when we were first developing block store. So here's some background again. We replicate puts between zones. So in this example, if you put to zone A, and maybe that block is supposed to be replicated to zone D, behind the scenes, that's going to happen. And we manage this by using a queue in MySQL, or on top of MySQL, I suppose, using an auto-increment index. And as we put data into block store, this queue fills, just like that. And that's what we normally expect. But there's a special case that's possible that we didn't know about, that we didn't assume properly of MySQL. And so it looks like this. This is still normal, but then boom, just for an instant, we skip an index. And then right after that, that empty spot could get filled. So this 1114 can get in before 1113. And this can happen under a case of concurrent puts. And that's because a write to MySQL with an auto increment counter, it's actually not atomic. You get the counter, and then you bump it, and then you commit. They're separate. So this can happen. And our code, or I guess when we developed the replicators, we didn't think about this. So in this case, where we wanted to replicate between zones, if we read out of this queue at the wrong time, then that skip key would actually not get replicated at all. And maybe this is like a once in every million bug. How do you find a once in every million bug based on incorrect assumptions in the tools you're using? Certainly not through testing. In testing, you have to know what you're hunting for. And our testing did not catch this at first. So how did we catch this thing? Well, we introduced a series of checkers, or we call them checkers. And these are sorts of monitoring systems that watch live state in production. So if you remember these are all of the main components inside of a block store zone. So the storage nodes that store the data, the block index that tells you which piece of data is on which storage node, and then the front end that does all the gatekeeping work. So starting from the bottom, going up, we'll have monitoring that verifies our state. So on the storage nodes, we have the scrubber. Every single storage node has a scrubber. And what the scrubber does is it walks over every single block that this storage node is supposed to own, and it reads it, and it checksums it. So we can confidently say what data that the storage node offers, it really can actually serve. But then we have to take a step back. That's not enough. So we have the scanner. The scanner walks over the entire block index. Our block index is MySQL. You can imagine like a full table scan here. And it does this continuously. And it answers the question, what keys we think we have in the block index, do we actually have the blocks? Are there storage nodes that can actually serve these blocks? And by answering this question, we can build internal confidence about block store, that all the state is accurate. But then we need to keep stepping back. This isn't enough. So we have the watcher. And the watcher sits on the outside. It makes no assumptions at all about the internals of block store. And the way it works is that when clients make successful puts, we log them. And then the watcher watches this log, and it rereads the same blocks at future points in time. ASAP, 1 minute in the future, 1 hour in the future, a day in the future, and a week in the future. And acts just like normal clients from that stateless tier of services. It also does this from the replicated zone. So all of these different checker systems, they're critical. They act at different layers completely. And we have several checkers at other layers. You can't skip a layer here. Every single layer needs some sort of verification system. So going back to my story, that bug, here it is again. The problem here was under concurrent puts, some rows can get inserted before other rows. So this 1113 would come after. Well, once we introduce the watcher, well, what the watcher does is after a put, it tries to reread the data. To the original zone, it works. And then it tries the other zone, the replicated zone. And it doesn't work. So then we noticed this, because the watcher screamed and paged us, and we found it. And this sort of system, this catches subtle problems. In our case, bad assumptions about how MySQL works. Without systems like these, you can't really catch these kinds of bugs. Testing isn't going to work. So that's really my sell here. But moving on, I guess, I'm still afraid. Like, we have these verifications, but what if something breaks through? Well, what do? The other side. We need to protect. We need to stop issues from getting to production first. And Blockstore does that through a gradual release process. We're really paranoid, so we make our deploys really, really slow. So we have a stage cluster of Blockstore. And what we do is we cut a release every single week. A release gets a week in stage, then a week in only one production zone, and then only after this do we promote that release to the rest of the zones. And this is a protection against software bugs. Our checkers are given the time they need to find the problems. So if we can have the release sit in only one zone and the checkers get a whole week, then we have pretty solid confidence around finding bugs. But what if bugs make it all the way into production? Release process won't protect us against that. So the next story time. Yay. So I'm going to help you put your paranoid hats on so that you can really worry about more subtle bugs, because they're going to happen. So here's some background again. Here's a slightly different diagram of the internals of a zone. Remember, storage nodes hold the data. The block index tells us which block is in which storage node. So we also have a node called the master that's responsible for some subset of the storage nodes. And sometimes we call it the janitor. It does janitorial work. It gives commands to the storage nodes, garbage collection, and stuff like that. What it does is it reads from the block index and uses information in the block index to know what to do with the storage nodes. And the way it does this is with a few steps. 1, get a snapshot of the state of the universe from the block index. 2, look at all of that state and then use that to decide what to do. Then give orders out to the storage nodes. And all of this is surrounded in one big master lock, or at least for us, we had one lock that was used for the entirety of the master. But for performance tuning, we wanted to reduce this, make several locks that are for separate use cases. So this lock changed, we replaced it. But there was a bug here, and we didn't protect everything with this new lock that we needed to protect. So in this case, with a particular type of state change, right at the wrong time, the master would analyze this data incorrectly and then command an incorrect delete to a storage node. This is, the real use case was a garbage collection operation regarding replication. If the block index says, these are the 3 storage nodes that should have the data, and there's another one that doesn't need it, it'll garbage collect. But here we'd incorrectly garbage collect on nodes that really should have that data. And for us, this manifested as a really rare race condition that would happen sometimes. Unlike the replicator bug, though, at least, our protections are already in place here. And that's the purgatory and the trash. So back to the nodes that hold state. Here, my main concern is delete operations. And the reason why is because the delete operation is, in a sense, an irreversible transformation. If you throw out the data, it's gone. So our protection is to try to make an irreversible transformation closer to something sort of reversible. So as expected here, let's say a delete comes from a client. It gets stopped at the block index. The block index soft marks the key for 30 days so that in 30 days, then we can actually go and delete this data. Then only after these 30 days can that delete propagate down to storage nodes. And the storage nodes, instead of unlinking the data immediately, they move this data to a directory that we call trash, and it sits there for 7 days. And only after those 7 days do we actually unlink the data from the storage node file system. So the key here is minimize irreversible transformations. And if they have to be irreversible at some level, then make them reversible until you have enough confidence that it is all right to indeed move forward with the deletes. So then, in our case, with this one story, here's a diagram again with that undesirable delete that the master did even though the block index didn't want it to. For us, the scanner system kicked in. The scanner was the system, the verification system that looks at the block index and then looks at the storage nodes. Here it said, hey, the block index has these keys, but what about the storage node? There's storage nodes that don't have this. And that's why we detected the problem. And fortunately, we could recover that data because of the trash. We can just go in the trash and go to the shell and do move back in and then hotfix the bug. So the moral here, you need protections in production against subtle bugs. The subtle bugs are going to come and bite you, so you need to go and build ways to recover from these sorts of incidents. So recap on the software bugs. Before production, verify and protect. Build tests and be really paranoid about your releases, letting bugs actually get in production. And then that's not enough. Subtle bugs are going to make it into production, and they're going to bite. So for us, we scan all of our state for consistency. And then we also use purgatory type periods to reverse or to make irreversible transformations less dangerous. So then the next fear, which is hardware. Hardware is literally a moving part, which is why I'm afraid of it. We have hard drives crash all the time. Power lines can fall down and take out data centers. So then what should we do about it? Oh, I'm afraid. Well, the same pattern. I'm going to try to bash this into you. Verify. Just like the software, we can't just trust it and shuttle it out to production. So when we are going to try out a new kind of hardware class, we test it with a pre-production qualification. We give it a workload similar to production, and we watch it. And that vets our hardware the same way our software tests do. But then we have the same problems as software. What if issues make it to production? So for us, we use sensors everywhere, and it's just like the software scanners, constantly checking the machines for invariants. And are systems like this enough? Clearly not. We also need to protect. And for block store, our redundancy is our safety. So I'm just going to emphasize this here. Zones are the systems that protect us against large incidents, because every single block lives in at least 2 of our zones. So broad incidents like earthquakes or that alien attack that I'm afraid of, but I guess none of you are afraid of. Then internal to a zone, redundancy between the storage nodes is what protects us. And having these different layers lets us keep small incidents actually small. Losing a single hard drive shouldn't make us have to recover data between zones. These zones need to be isolated. So protections at these different scales protect us against completely different classes of problems. So my cell here, layered defense is critical. So recap on hardware land, before production, in production, verify, just like software. And if anything can break any time, then you need to be redundant. So the next fear is a fear of humans. And humans are scary, like interns are scary. I guess interns are humans, maybe. Well, that was bad. I thought of that on the spot. But we can't control humans like we can software. And That's fine. And a particular problem here is that, in a sense, they're non-deterministic. Verify doesn't perfectly fit the model here. Usually we verify these systems to try to catch these bugs before they can make it out there. Operators don't really act like that. They'll make a mistake once, and that'll be the mistake. And I'm afraid of that 1 in a million mistake. So I guess what I'm trying to say is auditing everything operators do, I don't think it's a valuable use of time. So the focus here in this section is going to be all on layering up protections. So story time, yay! Woo. So once again, we got to take a step back, keep things concrete and real. And so here's the next story. So we have a notion of machine life cycles in Dropbox as a whole. And this lets us manage things like repairs or when we commission in new machines. So this life cycle equals allocated. Allocated machines are live. They're running real services. There's another life cycle. There's reinstall. And when we deallocate servers, they go into this life cycle for like reprovisioning or repairs or anything like that. And usually operating on this is all automated and we rate limit it and have some protections around that. But there was a day when we wanted to rush manual version upgrades. We had a particular reason for this. So here is the command that we used to upgrade these machines. GSH is like distributed shell, but it's our own in-house one. But this command was supposed to take these reinstall servers and upgrade all of them. But there's a mistake there. And that's that there are quotes missing before the word cache and after the word reinstall. So this part that's red now, that is the actual command that got run. And that lifecycle equals reinstall part, it got parsed as an environment variable and then essentially ignored. So then what happened? Every single lifecycle got targeted, and that took down the site. Because to upgrade a host, reboot it and do a bunch of stuff. So the site went down because of missing quotes. Simple missing quotes. How do you protect against this? Verify wouldn't have done anything for us. So let's layer up the protections. The theme here around humans, I guess, is to slow them down when things are unusual. So here's the first one in direct response to that particular incident. We want to gate operations that don't match some particular set of invariants that we have. So here's an example with block store. Block store zones are supposed to be completely isolated from each other as much as we possibly can. So a command like this, let's target every single storage node and upgrade them. This should not be legal because zones are isolated. Nothing should happen to multiple zones at the same time. So what we have now is a gate. We block it. Hey, you're not allowed to do it. If there's a good reason to break invariants, then the operator has to go and use multiple commands. At least they're really explicit about it. They're slowed down, not too much, but just enough. And I'm completely fine with making that trade-off. And by the way, I guess a plug, this GSH thing is open source, and the protections around it, or adding protections, is first class. That's thought of from the beginning. Here's another protection we have. That's on the host level, so zooming in a bit closer to the data. Remember, layered protections. So here's some command that one might run on a server. I hope not. But usually, to get into production, public-private key pairs authenticate us. And that gets us into production and all, and that's great. For an operation like this, though, what we do within block store is that we gate them. If they're unexpected, then you have to type in a password. RM is not a blessed command, so you have to type in your password. You're a bit slowed down, you have to type in some stuff, it's a little bit annoying, but if there's a good reason to break the invariants, I'm fine with this. I want to slow you down. And this can protect us in many ways, especially if you just hit enter and you notice like, why is it asking me for my password? I thought this was expected. No, you misspelled it and you're actually going to delete all the data. You had to type in your password, so it stopped you. Sweet. So similar idea as the other, slow operators down. But even then, so I put an empty slide here so you'd focus on me speaking, I guess. But what is it that I'm really afraid of? Is it just shell commands? What about config management? Someone committing something that reformats the wrong hard drives, or cron. There's so much out there that can mess with machines that can run, and it's hard to really attack them one at a time. So what did we do about this? we use Tomio. What is Tomio? So Tomio is a kernel module for access controls on the system call layer. So for us, only storage node code and special whitelisted tools are allowed to do mutations to data drives at all. So here's an example. I'm going to try to remove a block. And it's not going to let me. And this is different than the previous example. The previous example was that rm, the command, was not blessed. Here, my shell as a whole is not blessed. And it's not just that this one command doesn't work. Here's strace output. It does not let you do it at the system call layer. So if the operating system layer denies this, then we have this broad net of protection that can protect us against so many different types of problems. And that's why we have this. And then you think, why do we need those other protections then, if Tomio is so cool and spiffy and stuff? And that's, again, defense at different layers. Tomio, for us, Tomio is only good for protecting against mutation in the data directory. But, for instance, what if the host goes through mutation where it's rebooted? Tomio is a kernel module. It might not get loaded and won't protect against that. So stuff like distributed shell gating and pseudo passwords protects us against different problems at different scales. So, recap on human error. Well, verify is pretty inefficient, not too useful. So instead, layer up the protections. Slow people down and gate what's non-standard. My next fear? Automation. And that's because automation is like super, super aggressive humans. They move way faster. And the thing that scares me the most is automated tooling that decides to go and reformat all the hard drives because supposedly they're all messed up, but they might not be. So what should we do? Well, let's follow the pattern. Let's start with verifying. Automation reports. Logs. How often do the tools run? When do the tools raise exceptions or discover situations in production that aren't completely the usual? Email reports and such are really simple and effective. And the goal here is to spot possible dangerous bugs when they only make small bytes. But if we find them when they only make these small bytes out of us, then we can stop them from making these big bytes that really, really hurt us. Next, a note on tooling. These are some 3 steps that a lot of people think about with tooling. Like, you do stuff manually, you script it away, but then you run the script, and eventually it runs itself on its own, powered by cron or something. I don't think this is quite right. And I guess that's just because I'm paranoid. I like to throw protection around it. And that's for high-risk automation. Humans are required to sign off on the operations before they run. So how does this manifest itself for block store? Well, first, tooling goes and diagnoses the problem. There's this medical analogy that I tried to make that sometimes people understand. But the diagnosis pokes the problem, and it comes back to the human operator and explains it. So here's an example. Something's wrong with this hard drive. And I, the tool, figured it out by doing this. Here's what I experienced as a tool robot creature. After the diagnosis, there's a prescription. What is it that should be done to fix this problem from the diagnosis? And here's an example. Well, that disk, clearly we can't use it, so let's decommission it. And this is the exact command that we're going to use. Then there's the actual human authorization part. The whole point of all this. The human has to say yes. And so I forced everyone to type, yep, that evidence seems legit, and then I'll run. Oh, derp story, because someone's going to ask this. The code checks if standard in is a TTY, because my coworker Scott McFiggin was trying to cheat around it. Oh, humans. But even with this, humans can't do all of the policing. This isn't going to completely scale, and humans can't watch everything. So we also have the tools police themselves. For us, the critical case is that data needs to be replicated in order to do dangerous actions. Here's an example. Deallocating a storage server. That's like a weird made-up host name. See the ABC in the front? Clearly fake. Well, here's an example of a time when this wouldn't work. I'm blocked because for every single block on this server, it's not perfectly replicated elsewhere. We need to wait for perfect replication before we even try to take this slightly sketchy but not too dangerous operation. But that's just because I'm paranoid. And really a way to think about this, a step back from block store, is that if we detect signs of some potential accident out there, then let's freeze the system as much as we can. And that creates fewer moving parts, and so there's a lower chance of accident. Then another note I have, which is that tools aren't so different than the normal software we run. Tools need to respect isolation and other protections just like the software does. So for us, tools only touch one zone at a time, or they have that protection that I mentioned just before. Sometimes I think people don't really treat their tools like they do their core software with the same level of concern about it. They treat these tools like they're something different. I don't think they are, and I don't think any of you should treat them like they're something different. So, recap on automation bugs and such. Logs, you need reports, you need to know about potential sketchiness, possibly upcoming in the system. And then protect, well, add the human touch. And then also freeze the system if you see any potential danger possibly happening. Then finally, my last fear here, which is the protections themselves. And what is it that I'm afraid of about protections? Well, what if they turn on me? Or what if they don't actually work? That's pretty scary. Why would you even do all this stuff if it doesn't even work? So what should we do about this sort of fear? The same thing as always, verify. So disaster recovery testing or training, I never know what the T means. But SREcon's super obsessed with this, so I don't want to dive too deep on it. But the core idea is that we induce failures in production to test that our fault tolerance and our protections actually work. And in the end, that just means you need confidence that your protections are really going to work when you actually need them. Or else it's not going to work when you really need it because the universe likes spiting me. That's it on verification here. My other fear is protections making things worse. So we protect. So when you're really in trouble, you can't let your protections slow you down. You need some way to disable the protections or get around them. Here's one example. For Tomoyo, you can imagine like Tomoyo creates an issue where it actually blocks storage node code by accident. Suddenly nothing works. Well, here's a command for us that will disable Tomoyo on a single server. And we can use this if we really, really need to. Overrides like these, we absolutely want to avoid them. But just in case, in that rare circumstance when Tomoyo comes and bites us, this could really come and save us. So, worrying about protections, well, verify your protections. It's code just like software, so test them, preferably in production in the most real case possible. And then also have ways around your protections because protections can often bite you back. So, recap on the entire talk because I've made all of my core points, I guess. So, find your fears and really embrace them. Then think about prioritization. You can't worry about everything. Chance and severity are what matter. Prioritize these things. Then take your fears that come out of this and verify them and protect them. Both of these are necessary. Thanks. And yeah, I can take some questions.
What prevents a malicious or compromised user from using the overrides?
When you say user, do you mean employee?
Yes.
So the protections that, or I guess with regards to malicious employees, you're concerned about security, right? So these protections are about durability. These aren't about security, and we have a completely different set of verifications, protections around security that I don't work on. But for this at least, for the durability protections, we don't worry about malicious employees. But for the security protections, we absolutely do. And we do this by having very few people who have access to these sorts of controls. And I can connect you to a security engineer if you really want specific examples.
Hey, protecting against human definitely increased friction in day-to-day job. Have users complained, and how you dealt with that?
So first of all, I guess the only people who have access to the block store nodes and can do operations on them are the block store team. And inside of the block store team, we certainly have had some friction where some people think that they're slowed down too much. For instance, I had a case where I wanted to just remove a log file because I created it on every storage node with the wrong permissions. And that slowed me down a lot. For me, it's worth making that trade-off. And I guess I take a stand and say, these protections are really, really important. And so you're just going to have to deal with it. And in some cases, we do rethink it. We step back, and it goes back to that chance versus severity. What are we really protecting against? If we have some protection that's not actually protecting against anything really valuable, then it's completely fine to remove it. But with regards to absolute focus on durability, I'd rather take a stand and lean towards stronger protections and slowing people down more.
Is there anything stopping somebody from running the override Tomio policy besides having to actually type it out?
For us, no. You have to type it out. You have to run it across all the hosts. In general, there's a notion of you disable the Tomio policy, and then suddenly tons of tooling is let loose upon the system. In the end, we imagine the Tomio policy will protect us against maybe 1 or 2 incidents for a whole year. And if you disable the Tomio policy, it's not too troublesome if it's only in the short term, and we'll be alerted per host that Tomio policy isn't running, and then re-enable it. But we don't have too much friction there. I'd rather not have too much friction because then I'd need override around the protections around the override, which then I'll add another list to the list of fears. Or, yeah.
Hi, so great talk. I had one question. You talked a lot about making it hard to do the wrong thing. What have you done at Dropbox about making it easy to do the right thing?
So I say this comes to building tooling. So I guess the question in general was, how do you make people do the right thing as opposed to preventing them from doing the wrong thing? And I think by building tooling, we can make people stop worrying about the fine details. So for block store, there's that command that was bsctl. It's block store ctl. I say ctl. Some people say like control or whatever. And that's a single gateway to operations. People shouldn't worry about the fine details of like writing tons of command line flags. For really standard operations that people do all the time, bake it into a tool that's really, really easy to use. It's part of this whole, I guess, infrastructure as a product idea. But yep, it all comes down to tooling, I think. No other questions? All right, thanks a ton.